So welcome back. This is the last section of the moles 2 notes. And we're going to be looking at combining combustion analysis with PV equals nRT. And we're also going to be looking at percentage yield and atom economy equations. When you finish those bits off, then you'll be able to answer all the questions at the back of the pack. So we're on page 12 of your notes, and we're looking at a compound which has a percentage composition by mass of this, and then if I took a 0.173 gram of the compound and I measured its volume and pressure and temperature, I can then use that to work out the molecular formula of the compound. So the first thing I've done here is I've just done a little empirical formula calculation that we've practiced a lot in the previous topic. So I've got my mass divided through by my RAM to give my moles, and then divide through by the smallest to give me the simplest whole number ratio. So my empirical formula is going to be C2H6O. But I don't know if that is my molecular formula. I need to use my PV equals nRT data to work that out. So again, same thing I've done before. I'm going to write down P, V, N, R, and T, and I'm going to add in the values that I know. So I've got 105 kilopascals. Well, that's 105 times 10 to the 3 pascals. My volume is 95 centimeters cubed, so it's going to be 95 times 10 to the minus 6 meters cubed. N is what I'm trying to work out. My R is 8.31. My temperature is 45 degrees Celsius, so that when I've added on my 273 is going to be 318 Kelvin. I know that N is equal to PV divided by RT. So I'm going to put these numbers in and I'm going to solve for N. And when I do that, I get 0.00377 moles. I know my number of moles from my question. I know the grams of compound, so I can work out my RMM, and that's going to be grams per mole. So I've got 0.173 divided by my number of moles, 0.00377, and that gives me an RMM of 45.9 grams per mole. So my empirical formula mass is 46 grams per mole, and this is very close to the 45.9 grams per mole, which I've worked out using PV equals nRT. So therefore, my molecular formula is the same as my empirical formula, because it is C2H6O. So my second example, I've worked out the first bit, same as I've done before, using my simple empirical formula calculation. And I've got an empirical formula here of CH2O. Again, I'm going to use my PVNRT to find the number of moles. That, with the mass, will give me the RMM. So I've got a pressure of 98 times 10 to the 3 pascals. I've got a volume of 69.5 times 10 to the minus 6 meters cubed. Notice I've just converted them directly into the SI units. My N is what I'm trying to work out. My R is 8.31 and my temperature is 336. It's always a good point to work these out, because you get marks for turning things into the correct SI units. If you just plug everything into your calculator without doing that step and without showing that conversion, you're likely to lose one of the marks. So again, I'm just going to stick all of those into my calculator. So N is equal to PV divided by RT. So I put those numbers into my calculator and I get 2.439 times 10 to the minus 3 moles. Again, I can work out the RMM because that is going to be grams per mole. So I know my grams, know my moles, so I can work that out. And I get 59.85 grams per mole. Now you can see it's roughly double the empirical formula mass, or at least within the limits of my experiment. So I can therefore say that the molecular mass, the molecular formula, equals twice the empirical formula. So therefore we've got C2H4O2. So the last question on page 13, this was an old exam question that was asked a few years ago. So I've got a known mass of compound X was burnt, and I know the masses of the carbon dioxide and the water. So I can work out the amount of carbon, hydrogen and oxygen. So I'll do this in exactly the same way that I did my combustion analysis earlier on. So I've worked those out there in exactly the same way I did before. Mass divided by RMM to give me the number of moles. Well, there's 1 mole of carbon for every 1 mole of carbon dioxide, so times by 12 to give me the grams of carbon. Do the same for the hydrogen in the water, remembering this time times by 2 because I've got 2 moles of hydrogen per mole of water. To find the mass of the oxygen, I'm going to take my total compound and take away the masses of the carbons and the hydrogens. What I can then do is put those into a little empirical formula table, just as we've done before, and we come out with an empirical formula of C2H6O, and that has a mass of 46 grams per mole. In the next experiment, I'm going to be using PV equals nRT data to work out the RMM. So I've been given my mass, my volume, my temperature and my pressure. This time the only one I need to convert is this centimetres cubed into metres cubed, and I've done that here. Put those into my calculation and I get the number of moles. Mass divided by moles, grams per mole, gives me 46. So therefore the empirical formula mass is equal to the molecular formula mass. And therefore the molecular formula is the same as the empirical formula. It's C2H6O. We're on to this last section of the notes, looking at percentage yield and atom economy. Now before we do that, we need to understand what is meant by the limiting reagent. In chemistry, it's very unusual that we react exactly the right amounts of each reagent. Quite often we have one reagent in excess and one which is our limiting. Now, all the calculations are done with the limiting reagent. That's the substance which will determine the theoretical yield. And we need to understand and learn this little equation. So percentage yield is the actual yield, so how much you actually get, and that's always measured experimentally. So I can't determine that any other way. I've got to actually physically measure it. And my theoretical yield, which comes from the idea that, okay, if everything reacted, if I got 100% conversion, that would be the maximum yield. That would be my theoretical yield. So let's look at an example of that on the bottom of page 14. We're asked to work out the percentage yield of sulfur trioxide produced in this reaction. So the first thing I'm going to work out is the RMM of my sulfur dioxide, and that comes out to 64.1 grams per mole. So if I started with 1,000 grams of sulfur dioxide, I could work out the number of moles, therefore, of sulfur dioxide that I started with, and I've got 15.6006. Now it's a 1:1 molar ratio between the sulfur dioxide and the sulfur trioxide. Therefore, the theoretical number of moles of sulfur trioxide is the same as sulfur dioxide. The theoretical moles assumes that none is lost, there's no side reactions, no escaping of anything. I got everything converted perfectly into product. Well, the RMM of sulfur trioxide is 80.1. So therefore the theoretical mass is my moles, 15.6006, times by my RMM, 80.1, and I get 1,249.6 grams. So the actual yield of sulfur trioxide, how much I actually got, was 1,225 grams. So what I need to work out my percentage is my actual 1,225, which I actually got, divided by what would have happened if I got everything converted, 49.6, and I get 98%. So that's a very high percentage yield. So the other way of working out the efficiency of my reaction is to look at the atom economy. Now the atom economy is the mass of the desired products from the equation divided by the total mass of products again from the equation, times by 100, turn it into a percentage. So let's look at an example. The atom economy for making hydrogen by reacting coal with steam. Well, I need the equation, and I need to have a nice balanced equation. So I've got carbon, 2 waters, 2 steam, reacting to form 1 carbon dioxide and 2 hydrogens. So I'm going to write out my equation, and underneath it I'm going to write out either the RAM if it's an element or the RMM if it's a compound. And I've got 2 moles of hydrogen, 2 moles of water here and 2 moles of hydrogen. So I do need to use this balanced stoichiometric equation. So the total mass of the products is the 44 grams of carbon dioxide and the 4 from the hydrogen, so I get 48. Now that must be the same as the reactants because I can't have lost any of the mass. So the mass of the desired product, what I want, is my hydrogen. So therefore my atom economy is my 4 divided by 48, which gives me an 8.3% atom economy. That's not very high. So making hydrogen via this method, even if it had a high percentage yield, would not have a good atom economy. It would not be a good way of making hydrogen. So that finishes these notes looking at moles 2. We're going to take a little break from moles in the next topic. We're going to be looking at groups 1 and 2. But we will be returning to moles later on in the year to look at the moles of solutions and look at our titration experiments. So until then, take care, stay safe, bye-bye.